You should
So
start.
something
Otherwise,
non-trivial
we
must
can
happen
continue
with this
talking.
phi, I mean.
Okay, so let's start with the last hour of your lectures, and that's it. Let's go.
All right. So I think, did you want to say something? I think you appeared just to say something.
Yeah, I wanted to say that the sign of the beta function depends on the symmetry class. And if I remember correctly, at one loop, it's so the beta function is 0, and then it depends on the symmetry class.
Yeah, that's
but there
right.
you additional symmetries, and you are probably already in the nonlinear sigma model, no?
Yeah.
No, well, yeah, but I think maybe the beta function will be the same for, well, maybe not. Yeah, I'm not sure. Yeah, in the sigma model, we certainly know how it differs by the symmetry class.
So you mentioned yesterday, Ilya, that for random fermions, Dirac fermions with random mass, the disorder is marginally irrelevant.
Mm-hmm.
So that's class D.
Yeah.
And then for class C, I think the disorder is relevant.
Mm-hmm. Mm-hmm. All right,
and
so maybe it's a good place to actually start talking about this symmetry classification. That's important, just for the people to know that there is such a thing. So the story is old in a sense, because in the context of the nuclear physics, Wigner and Dyson studied various random matrices, right? And random matrix theory had traditionally classifications of possible Hamiltonians of random nuclei or nuclei as random matrices in 3 classes, right? So Wigner-Dyson classes were identified, and this is what's called unitary, orthogonal, and symplectic. And the story is that essentially what they realized is that you can think about all possible physical symmetries being broken, in particular if time reversal is broken, then what happens is that the Hamiltonian is not constrained at all, except that it's a Hermitian matrix, right? Then so you can then study random Hermitian matrices which are invariant. The symmetry distribution that you can write for the Hermitian matrix is invariant with respect to unitary rotations of those matrices. So the name unitary for this class comes from the invariance of the ensemble of random matrices under unitary transformations. Okay, in particular, unitary transformations preserve the spectrum of the random matrix, and this is mostly interesting stuff is to study the spectral correlations in these cases. All right, now if T is preserved, then things fall into 2 classes, because this can be time reversal symmetry can be written in terms of the complex conjugation and some anti-unitary operator, and that anti-unitary operator itself can square either to 1 or -1. So there are several cases, and in the case of in quantum mechanics, when you look at the particles with spin, one case corresponds to integer spins, the other corresponds to half integer spins. And essentially what happens is that if you look at the spinless particles or particles with integer spin, then the condition that you get on the Hamiltonian, in addition to the hermiticity, is that it's in some basis at least, it's a real Hamiltonian, right? So it's equal to its transpose. And then another option is that it can be related to its transpose by some rotation in the spin space. Well, you have this extra structure in this case, right? So these are 3 Wigner-Dyson classes, and the fact that they're related to any nonlinear manifolds or sigma models can actually be easily seen by the following argument. that if you think about the I times H being an element of the Lie algebra UN, then this UN is a target space, is a tangent space to some group, right? And so it looks like when you have no constraint other than hermiticity, you're dealing with the targets with the tangent manifold to a group manifold. So this group itself, so that is the so this UN itself can be written as UN cross UN mod UN. So that's some kind of a coset space, which in this case is not. It's just a group itself. But these other cases, when you have this structure that this matrix is, let's say, real, or this kind of matrix, the corresponding spaces of Hamiltonians turn out to be tangent spaces to real cosets. And in the case of the orthogonal class, the corresponding coset space turns out to be O2n mod UN. And for the symplectic class, it turns out to be a symplectic group, unitary symplectic group mod UN. So,
sorry, Ilya, I'm not following this. What are you talking about now?
I'm talking about the connection of this Hamiltonian to the symmetric spaces.
But so there's many levels here. Ultimately, there's the level of the field theory. Right now, we're doing the Hamiltonian.
UN, I need to. Sorry, I made it.
Thank you.
Yes. So this is what, and the other one is probably also incorrect. Sorry. Yes. So I wanted to make, of course, sorry, UN mod SPN. Let's put it this way. Right. Okay, maybe I'll just say in words that the program that I was sketching of the derivation of the sigma model can be extended to the random matrices easily, because a random matrix can be viewed as a Hamiltonian zero-dimensional space, and you can do the same trick. You can study its resolvent. You can write the corresponding Green's functions and everything, and that will result in a single supramatrix integral. There will be no space involved, and this super integral will be over certain supermanifolds, right? And in using replicas, you would get the manifolds that I have here. Okay. Now, what Untitled and Zirnbauer realized is that there's more to this story, because you can now add additional symmetries to the problem. In particular, there's a class of problems called the Chiral Classes, where the example would be a lattice tight binding model where the particles can only allow to hop from one point to one sublattice to another with a bipartite structure. So you have something like sum over I and j, Tij, Ci dagger, Ci dagger, Cj, plus complex Hermitian conjugate. Then this Hamiltonian, at least in some basis, which is appropriately defined, will look like a block diagonal matrix with only blocks here and here, and zeros on the diagonals, right? So this is an extra structure that in particular tells you that energy, eigenvalues, for example, come in pairs, plus minus E, and the zero energy plays a special role, right? And so then close to the zero energy, you may have some extra physical phenomena that may be special to this particular arrangement. So these are called chiral classes, and there are also 3 of them. And if you focus on the physics close to zero energy, that symmetry requires extra attention and leads to different symmetry classes, different sigma models, and different structure of the target space. And finally, there's a Bogoliubov-Dejean classes, which describe mean field theories of superconductors. So for superconductors in the mean field theory formulation, the Hamiltonians may include this non-number preserving terms of the type, we have sort of Ci dagger, Cj dagger, and there's some coefficient which is related to the order parameter of this theory, plus Hermitian conjugate. Plus in addition, you can have also usual regular number preserving terms. And these, so these Hamiltonians also have the special form in a particular basis of some block diagonal matrix where the diagonal parts are now responsible for these superconducting correlations, and the off diagonal parts correspond to hopping. And again, the same story goes that these classes have to distinguish furthermore by the presence or absence of time reversal invariance and spin rotation symmetry. So there are 3 classes here and 4 classes here. So in total, we get 3 Wigner-Dyson, 3 chiral classes, and 4 Bogoliubov-Dejean classes. In total, 10 classes. And these classes, each of them correspond to its own family of Riemann superspace. So if you carefully derive a sigma model using all these symmetries and necessary ingredients, so for example, you have a particle hole symmetry of the type in the chiral classes, you have to enlarge your space, you have to include extra copies of your fermions and bosons, so this extra structure that gets tensored in some sense. And then your field theory grows and the corresponding structure of the saddle point manifold is different, right? So in particular, so this is called the AZ classification, Untitled Chapter classification, and it's exhaustively tabulated in all kinds of situations. So in particular, you know all the 10 symmetry classes for all 10 classes of manifolds for the sigma models in this case.
Yeah, just a question. So this Chiral and Bogoliubov, I can see connection with Anderson localization problem that you started with, but what these random matrices have to do with Anderson localization, I don't understand. Can you comment?
Oh, okay.
Why do you put all this together somehow?
Yeah. So let me. So sorry, I sort of kind of glossed over something that is kind of very. The thing is that let's say from the big picture point of view, a single particle Hamiltonian is just a random matrix. Okay, so that's the message. Of course, it's a very special random matrix. If you think about the tight binding Hamiltonians, they're sparse random matrices because they only connect sites close by. But that doesn't make it less. It's still a random matrix. So in a sense, the study of localization is an extension of random matrix theory. And it's been known for a long time that if you are thinking about a metallic grain of small size, right, then the extended wave functions in this grain, there's a level repulsion phenomenon. And this is exactly analogous to just the usual random matrix, zero-dimensional random matrix theory, right? So you can model these grains by zero-dimensional sigma models. And
no,
the
but
zero
I'm just
dimensional.
asking, I mean, I imagine that everything that has been already, like random matrices have already been solved in and out many years ago. So it's not a problem for us. There's no CFT here. While in the other classes, there is actual CFT that we have to study.
Yes, in random matrices, there's nothing there's no conformal symmetries. There are no transitions of that type. That's correct.
Yeah.
So,
okay.
well, maybe in some special cases, but okay. All I'm trying to say is that the symmetry classification is the extension of the Wigner-Dyson classification of random matrices. That's what I'm saying, right? But okay, so I think that's pretty much all I wanted to say about this. It's just I just wanted you to be aware of this, right? There's 10 big families of 10 big classes that needs to be studied. I don't know if Martin wants to add anything.
Just one sentence. There are 10 targets, and each of them has the potential for a critical point. Whether this really happens or not is a matter of dimension. But in principle, you have these 10 targets. So that's the playground to work with.
Yes, correct.
But I don't understand how these first 3 targets that did not appear from any fermionic Hamiltonian propagating degrees of freedom, what is the interpretation of those critical points?
Well, sorry, I don't know. What do you mean? This is so this case is just the usual single electron moving in the random potential with time reversal symmetry being broken. So it can be broken by a magnetic field, can be broken by magnetic impurities. So if the time reversal symmetry is broken, this is the problem. So it's a sigma model on a particular manifold that I wrote on the previous page, the unitary class. So I'm not sure what the question is really. So am I answering?
I mean, it's just my knowledge of condensed matter forbids me to make a link, because on the second page, on the next page, you're writing some models of hopping electrons. This I understand, and I thought that.
Well, let me write
a model. Connect, but this H equal H dig, I don't understand like what this H refers to.
So this H is the following. It's sum over I, J, T, I, J, C, I, dagger, C, J, plus Hermitian conjugate, plus the random energies on site. Sorry, C, dagger, C.
Okay, and then on the next page, when you don't have this, you don't have this random energies on site. You only have random P's and
exactly. That's the difference. Yeah.
I see. Okay, thanks. Now it's more clear.
And for each class, I can write a Hamiltonian that belongs to this class, right? And this, so in fact, the thing is that this symmetry classification is exhaustive. It's sort of it's a theorem again, that there's nothing else, right? And so that's all the potential targets are here, right? Okay, let me now switch to my sort of main subject, maybe, and the last subject is that of a multifractality. So this is the feature of the Anderson transition that I think is very interesting. And remember, I told you that there's a transition in energy that if you draw the energy, you have critical point. And on one side, you can have extended state. On the other hand, you have localized states. And the caricature is that this is like something sitting at one point, and the extended state is something that is extended throughout the whole sample. But what happens exactly at the critical point? That's the interesting question. And the answer is that the wave function at the critical point, let me try to draw a caricature for this thing in one dimension. So it looks like this at the critical point. So it looks like there's something at some position, then there's almost nothing else, and then suddenly it sort of spikes again. And these spikes exist on any length scale. If you zoom in, what I used to call empty space in between somewhere here, if you zoom in, you will encounter the same structure. So very complicated similar pattern that is best characterized as a multifractal. And so now I need to explain what a multifractal is. I said this word already many times. Multifractal. All right, so let me do the following. So first of all, I take psi absolute value squared, and that quantity is, well, it's a probability density for a particle to be somewhere, right? So that's a positive non-negative number. In particular, it's normalized to 1. So the claim is that psi squared d/dr is a probability measure. And what I want to do, I want to study this probability measure using the multifractal analysis, which is exactly geared toward this kind of situation where this density, psi squared, is very non-uniform, very, very non-uniform. It's very large somewhere, very small somewhere else. So what I want to do, I want to break my system into small boxes of size A, and the system is of size L. And I want to find the probability that particle sits in a particular box, Bi. All right. So certainly the normalization condition is just the sum of all these probabilities is 1. The number of boxes is simply L over A to the power D. But then what I want to do next, I want to now form the following combinations. This is capital P sub Q, which is the sum over the boxes of Pi raised to the power Q. Okay. So these are called, for historical reasons, these are called inverse participation ratios. Doesn't really matter what they call them. These can be thought of as moments of the wave function. So, all right. So if you average over disorder, as we usually do, then you can say that each pi, little pi to the power q, maybe contributes the same, and you just get multiplication by n. Let me deal with this object. So in principle, for a deeper study and understanding, it may be important to notice that these objects themselves are random quantities, and you may follow their full distribution functions. That's sort of the complication that I want to avoid for now, right? So I want to only work with average values of these quantities, and I want to look at how they scale with the system size. Well, I wrote the scaling relation. It's not obvious it should hold at all, right? But it certainly holds at the critical point. Maybe I should point out that I can easily estimate what happens in the limiting cases, and this is somewhat illustrative.
And can you explain why is this an interesting thing to look at? Like, I don't know, for the Ising model, we don't ask similar questions. Like
you do. Some of the people do, right?
But
And
anyway,
so
that's not the first question that we asked. The first question is what is the correlation function, things like that. But this is seems to be a very specific question. Why is this interesting?
No. I was trying to explain that it's not specific. These multifractals exist in any random system, more or less.
No, I mean, they exist, but you have to look very hard to find them. For example, if you just look at the conductivity of electrons propagating in your material, will you see this in the 2-point function or 4-point function of psi's or of electrons?
Yeah, so, okay. Well, maybe, I don't know, maybe some other people have different perspective. I have the following perspective here, that it's an interesting universal critical property that you want to understand. Just from theoretical perspective, it's in addition to having the usual localization length exponent and other critical amplitudes and whatnot, there's a whole infinity of exponents to be understood here. From a more physical perspective, these correlations of the multifractal wave functions actually affect the physics of interacting systems by the necessity that if you're looking at a system close to an Anderson transition, then the matrix elements of all kinds of interaction Hamiltonians have to be computed in those, eigenstates which are multifractal, and that leads to very complicated scaling phenomena of interacting systems. So that's another. So there are all kinds of consequences that I don't want to really even mention here. I don't know. Anybody wants to add anything else?
Well, I mean, now Slava brings up the Ising model. Compute the free energy of an Ising model on a gigantic square. Subtract the surface of that square times the bulk free energy, and subtract further the perimeter times the surface free energy. What remains comes from the four corners. The thing that comes from the four corners that will scale with something that involves the system. So as more precisely, it will be proportional to log of L.
Yeah, but that's not like the first. That's not the first observable.
Well,
if you have to teach someone about the Ising model, that's not the first.
I couldn't find out anything else in a short time like that.
I mean, you can come up with
a
zillion of weird things about the Ising model, but this seems to be the most important thing about this system. So I was curious, why is this so important?
And it would be proportional to the central charge, by the way.
Anyway,
remember I mentioned the Nishimori point.
Yeah.
So if you look at the Nishimori point, then powers of the correlation functions there, even the magnetization itself, exhibit multifractal scaling. And that was studied by Choker and co-authors. So that's sort of, it's something that is intrinsically present in a random system. And it's interesting. I don't know. I mean, maybe it's not the first question you want to answer, but it's certainly a question you want to answer.
But I would say the following up on yesterday. I prefer a variant of this setting which gets rid of the system size. Yeah, so that was a remark which I already quoted. I'm doing it again by Slava yesterday. We don't like to see the system size appearing in our scaling laws if we can avoid it. CFT works most easily for the correlation functions of local operators, possibly in the infinite system, and the system size is gone. So these are the most natural, easy things to understand. Of course, ultimately you want to do boundary conformal field theory and all kinds of complicated things. But the first thing to do should be correlation functions that make sense in the infinite system where the system size is not there. So I'm somewhat critical. I'm sorry, because the speaker, of course, wants to make a point and present something useful.
So Martin, maybe I can say, yeah, I perfectly understand your point, and I maybe again explain this somewhat later. I want to make one point here. So the unifying concept here is that of a probability measure. Okay, so that has nothing to do with any field theory. So I'm trying to say that what I'm defining here is not a field theory object. It's just a probability theory object. You have some measure, and then I want to characterize it in some way. Do you know any way to, not relate it to the size of the system? I don't. I do. You use a point contact to... No, not... Why are you talking point contact? I'm just talking probability measure, an abstract probability measure.
The problem with the probability measure is it leads to termination. Because the total mass is 1,
yes,
and this total mass has to be concentrated in the system size, more or less.
Yes.
You build in a systematic system size dependence, and that is That's okay. You can do anything that you want, but if you're talking to CFT people who want to bootstrap, you're not giving them the right observable to study. So that, sorry, I shut up now.
I have a related question. How to relate the spectrum to correlation functions? So the information which is carried by this multifractal properties, I mean multifractal spectrum, is it related in any way with to the correlation functions as we know them in CFT?
Yes,
yeah, that's a whole subject of this discussion that I'm hoping to have. But maybe we'll start with something simpler, some intuition here. So let me just continue, and maybe we'll go beyond my time. But well, let's see. So let me look at the limiting cases here. So the extended states are more or less uniformly spread throughout the system, and then each probability pi in each box will be equally, more or less equal to 1 over n, one of the number of boxes. And then if you follow this argument, then you get easily that the tau of q in this system will simply be a linear function of q, which is, sorry, d minus 1 times q. So this is what we call the non-fractal. There's nothing fractal about this. All moments scale with the simple powers, which are different by integers, right? So that's called, gap scaling sometimes. So nothing interesting. So in a localized state, on the other hand, what happens is that pi is, sorry, pi, all the pi's are non-zero only within the localized volume. So pi will be equal to the a over xi with xi localization lengths to the power d. And so if you use this, you will see that there's no system size, which, well, for me, this is the scaling variable. But in the localized states, the system size does not appear. And so this is sort of usually is stated as the spectrum being 0. Okay, tau q is called the multifractal spectrum. And at the critical point, the tau of q is usually written as this metallic part plus the correction, delta of q. And this is called the anomalous dimension and whatnot. I must confess that there is a way to formulate this problem without reference to the system size. Namely, you can look at scaling of the local probability or the mass of this probability of this probability measure, which is centered at a particular point, and you look at how much mass there is in a ball of radius a. And then this scaling turns out, well, I call this r, little r, radius r. The scaling turns out to be with some power, alpha, and this alpha depends on where you are, where you sit, where you put your ball in. So the alpha has a whole range of possible values, and these are called local scaling exponents. And in a complicated multifractal, you can try to simply sample different points and put these alphas in bins and draw a histogram of how often a particular alpha appears. So that gives you some distribution of these alphas, which is characterized by some f of alpha spectrum, so-called. Okay, so I don't want to dwell on this, but probably this is somewhat better, and maybe, so rigorous approaches to multifractals usually focus on this quantity. This avoids the use of the system size, as Martin wants to do. And then one can argue that this tau of q that I'm drawing here, I'm writing here, and f of alpha are related by a Legendre transform. That's the two phases of the multifractal analysis. You can do it either using the moments of the distribution of the density, or this local scaling. Okay, but okay, that's just an aside. Now, what I want to say is that in terms of these anomalous dimensions, well, yeah, let's see. How much time do I have? So, well, maybe that's not very important. So tau of q has some very natural properties, that it's a non-decreasing function, and it has certain convexity properties that are encoded in its second derivative. So typically, if you plot tau of q, it looks something like, sorry, maybe I'll make it more precise. So tau, so there are some special cases that are given to you for free. If you look at tau of 0, it's just minus the dimension of the support of the measure, and tau of 1 by normalization is just 0, right? So if you put 1 here and minus d here, this is a curve that goes through these 2 points, and generically it's somewhat, it's not a straight line, it's something like this, okay? And there are all kinds of possible behaviors that happen for large and small values of q, which, okay, let me try to avoid this. It sort of will take us far away. Okay, what I want to argue now is that this application of these ideas to wave functions can be phrased in terms of local observables in the field theory, in that sigma model that I was trying to draw. And the idea is that you look not at the wave functions, but the density of states. And the density of states can be written in terms of the wave functions, of course, but let me, it involves local density of states, would involve some delta function. So it'll be the sum over the spectrum of the delta function of the energy, and then you would get the wave function squared there, right? I want to now think about somewhat smeared structure in the spectrum. And the way to do it is to think about some open system. Instead of closed system, I open system slightly so that the energy levels acquire finite lifetime. And then the smeared density of states will look like, so each delta function will be replaced by a Lorentzian for the corresponding. So it's going to be some regularizer here, something like this, okay? And then if I imagine that I have a very large system, then my level spacing in this system can be much smaller. So the level spacing delta, mean level spacing, is given by the inverse density of states. So it's sort of inverse density of states at a particular energy divided by the volume. So I want this density, so this mean level spacing, to be much smaller than my smearing, okay? Then what happens is that, roughly speaking, it's a very hand-wavy argument. It can be made more rigorous, but I'm trying to make it simple and fast. So if you focus on a particular energy, a critical energy, let's say, you want to sit close to critical energy. In a finite system, there are many states that can be called critical, right? Because even if you change the energy slightly, you already on the localized side, for example, and your state is formally localized, but its localization length is enormous. It's much bigger than the size of the system. So that on that scale, it's still critical, right? So there are many states that contribute to this local density of states, and I assume that they are somewhat statistically similar, and I can pull out this psi squared out of the sum. And then the sum reduces to the global density of states. And so the hand-wavy argument leads me to say that the local density of states in a smeared system is sort of like the wave function amplitude times the global density of states. So that's the main relation that allows me to do that. Strictly speaking, what you have to do, you have to go through the Green's functions to get any practical procedure, but it works. And in the end, it's the moments of the local density of states that map to operators in the field theory. And this can be, indeed, this whole mapping to the sigma model can be made in the presence of the insertions in the functional integral. And you want to look at a specific, power of the density of states, you can do that, all right? And out comes some specific operators in the field theory, which I schematically will sort of write as the local density of states. I don't really need the smearing anymore here. So let me just write the local density of states at the critical energy, and I take this whole thing to the power q, and that corresponds to some operator in the field theory. Okay. And the scaling dimension of this operator is related to the multifractal spectrum. That's the message. So now this average indicates the field theory expectation value. So that scales as L to the minus X sub Q. In particular, the density of states itself can be singular in some of the symmetry classes that I mentioned. In the Wigner-Dyson classes, this density of states is non-singular, but in some other classes, it is singular, and it scales in a finite system with the density of states exponent, which in some cases is known exactly. So X nu. So for conventional classes that people have been for Wigner-Dyson classes is 0, but it's non-zero for some other classes. So in the end, what happens is that you can look at the behavior of the moments of this wave function, or the probability of electron being in a box, and the ultimate relation is that this tau of Q multifractal spectrum is related to the, so that's the, I think I had an incorrect formula earlier. So this is the relation between the exponents here. So once you know the field theory exponents, the scaling dimensions of these operators, and x nu is simply x1.
Ilya, can I mention, maybe you can, so you put me in the right context. When we looked to the problem of a particle in a random potential that is logarithmically related, actually this dimension, this problem seems to be related to the Liouville theory in 2D, and these dimensions are given just by the charge of the Liouville theory is related to the temperature, and this xq is just the dimension of the vertex operator.
Yeah, so I don't know the exact context you were talking about, but it's certainly
maybe like I think that in quantum mechanics a particle in a random gauge potential, and
yes, right.
And then you see the multifractal properties, and actually
sure.
this there is a sort of it is an old story that they have associated there is a connection with the Liouville theory.
Yeah, that's right. Yeah, certainly, absolutely.
Okay.
Yeah, but okay, maybe I'll mention this later. Okay, so I wanted to say something about this these dimensions. So that what's known about them generically is that first of all, x0 is 0. It's trivial, right? You get a trivial identity operator if you raise something to 0's power. What's much more non-trivial is that generically these xq behave in the following way. So it starts here. Well, it continues actually beyond this, but it goes back and hits another point, q star, where it also vanishes. So there exists some q star such that x q star is 0. So for Wigner-Dyson, already exhibited here, x q star is 1. For other symmetry classes, it has different values. It's known some numbers. Okay. What's important is that the corresponding operator is a very unusual operator with dimension 0, and it's not identity. Right. So the theory that describes this phenomenon has a strange operator that is not identity, and nevertheless it has a 0 dimension. Okay.
Why is it not identity?
Because the identity is identity, it's just 1, and this is not 1. This is
maybe this operator is also exactly 1. Whenever you insert it in correlation function, it's exactly 1.
No, it's not. It's not. I want to mention here the following point, that I don't believe that the field theory is exhaustive in the sense that all multifractal correlation functions can be even related to field theory. And the reason is that you can certainly define multifractal correlation functions just conceptually without any reference to field theory. And they behave not like field theory correlators. They just defy description in terms of field theory correlators. But some special combinations of multifractal observables behave like field theory correlators. And those can be related to field theory and conformal field theory. So let me give you an example. So let me take two operators, which are these multifractal operators. Okay, and sorry, I'm being somewhat sloppy here in terms of I'm jumping between the objects and the field theory and just multifractal, just densities of, powers of local density of states. You can do this analysis without mapping to a particular field theory. Just in the spirit of a general renormalization group, you can think that the OPE of these two things satisfies the simple rule that you simply add these two powers when you fuse these operators. And you take something to power Q1, you bring in something raised to power Q2, and you bring them together, you get the sum of the powers. And then if you think about the correlation function of such objects from the point of view of just usual RG, in terms of eliminating degrees of freedom, not a particular field theoretic subject. What you have to do, you have to think about some points separated by a certain distance, R1, 2. And what you do with this object, you start RG from some small scale up to this bigger scale. And while you're running it from the microscopic scale to the scale of R1 minus R2, the contribution to this function will get, scaling behavior from the separate exponents of these two operators. But then when you reach the scale, diffuse according to this fusion rule, and after that, everything starts to scale with the unified scaling dimension. So what the end result of this argument is that it gives you the behavior of the type of the following type. So this may be microscopic scale involved in the first factor. I don't want to write it down. So, but the scaling ultimately, when you go to large system size scale, is the scaling with the combined dimension, the dimension of the combined operator. So if you want, it's a product of this type, Q1 plus Q2 minus XQ1 minus XQ2. And then L turns out to be to the power minus XQ1 plus Q2. So here comes the point. So I'm perfectly fine in measuring in any specific system. I can just set up a system of system size L, go to the critical point, and measure this thing numerically. So nothing prevents me from doing that. And I will encounter this scaling. And there's nothing wrong with that. But it's not a field theory correlation function, because that will either blow up or disappear when L goes to infinity, right? Because it depends on the system size. I can manage to kill this dependence on the system size by doing something of that type. I can do two things. I can first of all set up Q2 being minus Q1. Then the x of Q1 plus Q2 will be x0, which is 0, and I have, something that does not depend on the system size. But it's not a field theory correlation function either, at least not conformally invariant, because the dimensions of the operators entering here are generically different. So you have a two-point function of operators with different dimensions that does not vanish in the limit of infinite system size. Perfectly fine multifractal correlator. I don't know how to describe it in terms of field theory. It exists, it's non-zero, it's finite, but the operators have different dimensions. All right, but I can do something else. I can instead choose Q2 to be this special value Q star minus Q1. And in this case, something else happens. So this Q1 plus Q2 then turn out to be Q star. And this is also a zero-dimensional operator. So the dependence on the system size also vanishes in this case. But then I get operators of the same dimension. And so this is a symmetry property that can be rigorously justified within the sigma model. Using the symmetries of the target space. So there's a derivation of this that I don't really have time to present, which works, which is a consequence of some special symmetry of the target space of the sigma model. So the operators that correspond to the powers of local density of states in the sigma model are related by this symmetry, and their dimensions must match. Right? So this relation exists for all 10 symmetry classes, but then there's some subtleties when and how you can use it, whatnot. Okay, but in the last 3 minutes, let me just say, so I have much more details in my notes, so hopefully you can just read them and we can have a discussion. I wanted to state this, that if you now think specifically about two-dimensional conformal field theory. And you assume both the abelian fusion that I wrote, when the indices of these operators add up when you fuse them, plus you assume that these are primary fields of your two-dimensional conformal field theory. Then you can study a 4-point function of these operators such that there's some neutrality condition. So you study things like Q1, Q4, but such that the sum of Qi's, is this Q star. Sort of neutrality conditions, very reminiscent of the Liouville and boson, free boson theory. Then this 4-point function certainly has only one conformal block because of the abelian nature of the fusion. And you can study this conformal block by using different channels. And then they're, of course, related by the crossing symmetry. It's the same function that satisfies certain properties. And in these limiting cases, when you fuse in a particular phase, in a particular order, its dependence on the cross ratio will have a power law structure. And these powers will depend on the dimensions of the operators. So roughly speaking, this conformal block has, this is now the cross ratio eta, has the branch points at the origin at 1 at infinity. And what happens is that the corresponding singularities are related. If you go around all 3 points along a contour, you can shrink this contour to 0 by going to the opposite side of the Riemann sphere. And so that gives you some condition on the dimensions of the operators. So these are known long time ago from Waffa and Llewellyn. But in this particular case, these conditions uniquely define the conformal block and give you some constraints on the dimensions that I guess I can find them here in my notes and write them once. It's some nonlinear equation that looks like this. Maybe I'll write it down somewhat. So it's x of q1 plus q2 plus q3 minus pairwise guys q1 plus q2 minus x q1 plus q3 minus x q1 q2 plus q3, and then plus the individual guys. And that turns out to be 0, okay? So then using this, you can easily get a consequence that these functions of Q are quadratic functions, the quadratic polynomials. This is the only way to solve this equation, is that this x of Q is a quadratic polynomial. And furthermore, using the symmetry property that I advocated, this quadratic polynomial is nothing but b, some number, times q star minus q. So that's the outcome of that story. Specific values of b, of course, depend on what particular fixed point you're sitting in, and q star depends on the particular fixed point you're sitting in. But the upshot is that the conformal symmetry seems to restrict these spectra considerably to parabolic form. And as such, they can be modeled by Gaussian free fields. And in Martin Zirnbauer's theory for the integer quantum Hall effect, there's a sector of that theory that is a free field, and that's responsible for these multifractal exponents with some specific values of b and q star. And so he'll probably tell you more about this on Friday. What for me, the big question is the following: whether this can be extended to higher than number of dimensions, whether just the global symmetry, global conformal symmetry, can restrict multifractality to any extent. That's not clear to me. Maybe it can, maybe it cannot. But that's a very strong result, and you know, any deviation that you can see from it would probably imply that something is broken. Either the abelian fusion rule is not there, or the conformal invariance is not there. And that's something that, okay, let me stop here. I skipped a lot of things, but yeah, I want to stop here and open the discussion.
Thanks, thanks, Ilya. So you
welcome.
finish your talk with a challenge to the. So if there are questions, question time. It's open.
So I'm actually kind of confused because the beginning sounded very promising. You just wrote some field theory. There were some fields. Then it became a bit more complicated with the sigma model, but it was still some field theory that had some correlation functions in terms of fields and so on. Then,
Yes.
Okay, I could imagine that was something that could be bootstrapped. It just looked like some, maybe it was logarithmic CFT, whatever, but anyway, it's something which could definitely be bootstrapped. Then you just took out of the head this multifractality things. Sorry if I'm being a bit like trying to summarize in my confused way, but those things they were not made out of fields of the theory, so
they are.
They
are made of the field. Yes,
well,
so
anyway,
sorry.
It was not clear
Let me
from
make
your
it.
presentation that they're made out of fields of the theory because they just constructed those of some probability things and so on.
No. So okay, sorry. So this again.
How are they made in terms
statement.
of
So let me make a statement. So the multifractal formalism in general applies to much broader contexts. In this particular context of Anderson localization, the operators that describe the powers of the local density of states have perfectly explicit expression in terms of the Q matrix of the field theory.
But
Explicit
you did not write it down. That's what
I didn't write them down. No, I didn't write them down. It's not essential for my purpose, but they exist, certainly. They can sort of open the book, as they say, and find them. They're explicit expressions in terms of the field theory.
Okay,
so
but for example, then I don't understand how you can get operators of negative dimension because this field theory just has operators of positive dimension. Start putting them together. I mean, it's not clear to me how you will get something of negative dimension.
Well,
anyway, these operators, they seem to be weird operators. You're saying you are not.
Wait a second.
Sure
are you okay with negative dimensions in Liouville theory or the non-compact boson field theory? The vertex operators for those fields have negative dimensions for certain charges. So what's wrong with that?
There's nothing wrong with that in some particular theory, but in the theory that you started with, it was not clear how those things would arise because in your initial theory,
this is the closest analogy I know of. So these parabolic spectra are all seeming to come from some non-compact boson of some sector of the theory that looks like a non-compact boson.
But anyway, I didn't finish my question. So my question was like, as a bootstrapper, if I want to begin with something simple with this theory, you seem to like offering me this most complicated sector of this theory where nothing works, and I have to start with this. And can't you just like offer something simpler, which were things we know that are nice and simple, and we can hope to bootstrap them?
Well,
should I go straight to this
look, sorry. I must appeal to you as an expert, because I'm not a bootstrapper. So I'm just saying that I don't know much about bootstrap. So I hope something can be bootstrapped in this theory, but I don't know what, and I don't know
which
how.
Which correlation function should we look at? Like, are there some protected operators?
Other than saying that there's this supersymmetry that certainly protects things, I don't know what else. There's this structure of the supermultiplet of the stress energy tensor and whatnot, but I don't know much more beyond that.
Are there some correlation functions that are known not to depend on the volume? So that because we need to work on infinite volume in the bootstrap, so we have to bootstrap some correlation functions which don't depend on the volume.
Yes, they exist.
Certainly. I mean, I can, again, in terms of those local operators reproduce the local density of states powers, again, you have to form a correlator, which I did on the last page here, with the property that the dimensions add up to this special number, which is known explicitly for each symmetry class. Those do not depend on the system size.
So you're saying that this theory that you're proposing us to bootstrap, it has infinitely many operators.
Relative operators, yes.
And is Q a real number or an integer number?
Q, it can even be complex.
Q can be complex numbers. So
yes.
there are all these operators, and they're all in these correlation functions are can be studied in infinite volume.
Yes.
Wow, it's a very complicated theory. So.
Sorry. That's what it is. It's generic. It's
for example, what about
for Anderson localization? This is generic. This happens in all Anderson transitions.
But this structure is completely not visible from the field theory description you started with. I mean, if you just look at this Lagrangian build out of phi's and chi's that you started with before you pass to the sigma model, it's just like a normal Lagrangian. I can definitely study it in 4 minus epsilon dimensions. There's going to be a ton of correlation functions they can compute. And all of them will make sense in infinite volume. So that structure is completely not visible there. So I'm really puzzled how going from 4 minus epsilon to 3, this very weird thing will appear. Yeah.
Maybe I can say something. There is one feature that hasn't been brought out very clearly due, I guess, to shortness of time. And this is that the initial action, other than this epsilon term, which is there for regularization, is imaginary. But now look at this imaginary part. It has a hyperbolic structure. There's a piece coming from the retarded sector and a piece from the advanced sector, and the action is the difference. So you're taking the difference of two positive numbers and you're multiplying by I. And then you're taking a disorder average so that this thing makes sense. But the point I'm driving at, it has a hyperbolic symmetry. And the main challenge, the main thing to be understood is how to handle this hyperbolic symmetry correctly. This was an observation by Franz Wegener in 1979. I thought we sometimes call it Wegener hyperbolic symmetry.
Yeah, that's right. So I forgot. So Wegener was the first to derive the sigma model. That's certainly using replicas.
But that's not a sigma model. We're just looking at this linear.
Yeah. So, but Slava, if you feel that you can handle by 4 minus epsilon a theory of scalar fields, yes, but think about it again when you have this hyperbolic structure. There's a the manifold along which the action is stationary is not a compact manifold. It's a hyperbolic manifold, and that brings in complications that maybe you underestimate.
Most likely, yeah.
I'll try to make this somewhat clear on Friday.
But what goes wrong if I just like formally do perturbation theory in this theory in 4 minus epsilon dimensions? I'll get something, right? Some correlation functions. Do they have any physical meaning, or is it just garbage?
It starts with the following. People have looked for upper critical dimension, but the
it doesn't exist.
Some years ago was that there is no upper critical dimension. So
that's correct.
You have no business doing 4 minus epsilon. There's nothing, as far as we know. This may be wrong.
That's correct. There's no upper critical dimension for this theory.
No.
The closest to the mean field theory that you can get is to put it on a beta lattice, like an infinite dimension. So the infinity is the upper critical dimension. Moreover, there's no order parameter. There's a more basic thing. There's no order parameter. There's no symmetry breaking in this theory. Okay, So that's like no spontaneous symmetry breaking in a sense. And the closest to the order parameter that we can get is the full distribution function of the local density of states. And that distribution function behaves in a sense monotonously all the way to infinity. So there's no upper critical dimension.
No, I'm sorry, I don't understand. If I take here in this Lagrangian, if I take energy not equal to the critical, so energy is like the mass. If I don't tune energy, correlation functions of phi and of chi will just decay exponentially, and that's going to be it. So
yeah.
So
Certainly.
then I tune E to some particular value, they will decay like a power. That's the usual thing. So like, I think that would be a very interesting discussion. I don't know, maybe now it's not the time because we are all tired. It's been challenging set of lectures, but like if somebody could just like compare why this theory is not what doesn't follow usual phi to the fourth intuition that we are all familiar with. So in the booster community, we do CFT, but we're also pretty familiar with how phi to the fourth and the N models work. We think we also know a little bit about super mathematics because we are all have high energy background. So it's pretty puzzling to look at this Lagrangian to see that it's just going to behave in a very weird way. So it would be interesting to work it out.
What Martin said. So what Martin said, this Lagrangian still lacks something. So what I need to do, I need to add. So if this is advanced sector, I need to add minus phi r star phi r and add a. Let's see, it doesn't matter. In the fermionic case, it doesn't matter. I can plus chi a star chi a, so r. So once you start looking at this guy with the hyperbolic structure between the advanced and retarded sector and the bosonic space, then all hell breaks loose.
Well, it would be nice to look at the full Lagrangian, and yeah, and then we can evaluate what we can do with it.
But so somehow I can look up the references where the statements about upper critical dimension are explained. I don't think they are phrased in terms of this field theory. I think they're phrased in terms of the sigma model, but maybe one can trace back these difficulties here. Martin, can you say anything about this?
Not really. I'm skeptical. So the conventional wisdom in the community is, and the people that worked on it are Yefetov, Sasha Merlin. I also worked on this in the early going. The conventional wisdom is that you don't have an upper critical dimension. However, I'm not so sure anymore. So some of what we thought were firm foundations are breaking away due to the insight that is coming now from the integer quantum Hall transition. And I think this issue of, is there an upper critical dimension? And if yes, what is it, needs to be revisited. And I think if the conformal bootstrap community could get interested and help with their expertise and technology, maybe some progress could be made. It's actually the reason why I'm here. Otherwise, I'm not a boot camper, but that's one reason I'm here. I think that these things need to be looked at again, and it's possible that we're going to have some surprises.
Yeah, I will post the papers that discuss the upper critical dimension in this theory, but yeah, just I don't. Yes, Gina, you have a question, please.
Yeah, I wanted to ask you about the origin of this magic constraint on x's. On the last slide.
Yeah, yes, that's right.
Thank you.
Yeah. What's the question?
What is it coming from? How can?
Where is this coming from? Okay.
It?
Yes. So all right. So this object here, this conformal block, has 3 branch points. they come from possible fusions of the fields. It's a 4-point function, so you can fuse fields in 3 different ways that correspond to cross ratio tending to 0, to 1, and to infinity. And close to those points, you can certainly just write an expansion for this conformal block, starting with some leading power. And that leading power will only know about the dimensions of the fields that you fuse. All right, so it'll be 3 different powers, but then viewed as a function on the Riemann surface, you know that these powers cannot be independent, because you can sort of, maybe, I don't know how to draw these branch cuts properly, right? So the branch cut around one point would oops, I don't know how to get rid of this. So the branch cut around one point, going around one point, will pick up this particular phase factor that is associated with the corresponding exponent. And you can do this around any points. But if you do a big circle, that will add up these factors. On the other hand, that total factor has to be 1. So it's exponential of a multiple of 2 pi, integer multiple of 2 pi. And that is the constraint that this is coming from.
And you mentioned some Waffa paper?
Yes, that's right. There's Waffa and Llewellyn, 2 different papers that explain this in different language. And it's actually somewhat bigger story, because it can be extended to non-simple correlation functions where more than one conformal block contribute.
Okay, thank you.
So yeah, if you write down a nonlinear sigma model, usually it means that there is a broken symmetry.
Well, no. I mean, unfortunately, this is not the case here. It's let's okay.
No. It is. The point is that a retarded Green's function, on average over the disorder, and advanced Green's function are different. The presence of energy spectrum on the real axis causes a cut in the Green's function, and that cut has 2 sides. One side is the retarded, and the other one is the advanced Green's function. That is a symmetry breaking. The peculiar thing is that this symmetry breaking that has to do with supersymmetry and with replica, this symmetry breaking doesn't give you anything interesting in terms of critical behavior. That's something silly, something basic. The appearance of non-zero density of states makes a difference between the retarded and the advanced Green's function. The analyticity in the complex energy plane is lost. You can't go across the real axis. That is asymmetry breaking, and that is what gives rise to the field of the nonlinear sigma model. It's called Q. The field is called Q, and it is nothing but the difference between the retarded and the advanced. It's the discontinuity of the 2 across the real axis for the Green's function.
But maybe I can add something to this. So Kai, the point is that there are much simpler theories where you can see this phenomenon. Think about it, it's unrelated to localization. It's sort of a toy model somehow. You can think about a model with a vector order parameter, vector field, which transforms under a non-compact group like ON, 1. All right. And then it lives on a hyperboloid, not on a sphere anymore. And the symmetry breaking somehow would infer that your field extends all the way. So how should I say it? In a non-broken phase, the field should live everywhere on the hyperboloid. And you cannot regularize this until you break the symmetry explicitly by some infinitesimal field, and you force the field to live close to the origin of this hyperboloid. And then you can release this field and allow it to explore the whole manifold. and it doesn't seem to care whether you do it on the localized side or the non-localized side. So that in that sense, the symmetry breaking is not there.
Why is this relevant?
Opposing answers, no? One on symmetry breaking, the other not.
Sorry?
So
now
maybe
we
I
have
should
two
try-
contradicting answers. One is there is symmetry breaking, the other there is not.
So let me try again.
Yeah.
Go to the case of a ferromagnet. Let's have local moments. Now, local magnetic moments, we don't yet know whether they will order to cause a spontaneous symmetry breaking called ferromagnetism on the big scale. Locally, some magnetic moments form. Yeah. I don't know whether we can call this symmetry breaking in any way. So locally, the system distinguishes some axis, some local magnetization axis. And then the interesting question is, does this give you a ferromagnet or just a paramagnet? And now coming to our story, it's the same thing. You have sort of the field of the nonlinear sigma model is like the formation of a local magnetic moment. It's the formation of a non-zero local density of states. And this, yeah, so it's a little bit semantic. And this goes hand in hand with the retarded Green's function and the advanced Green's function being different. Their difference being exactly this quantity called the local density of states. Yeah, so this is like a preformed local magnetic moment. And now the issue is, does this order, this local order parameter, does that cause a symmetry breaking macroscopically corresponding to a metallic phase? Or if the symmetry is not broken, corresponding to an insulator phase with localized states?
But somehow the jump over the cusp, the non-analyticity, which gives you the density of states, is your order parameter.
Correct.
Local order parameter, so to
Local
speak,
order
right?
parameter.
Yeah. Mm-hmm.
Well, it's local in energy or in space?
No, in space. In space. Local in space.
The Green's function has a position argument, yeah? So we can localize this in space.
But this kind of comparison to non-compact sigma models, it seems to me a bit, yeah, not very convincing, because for your supersymmetric sigma models, the bosonic part seems to be compact, right? And
no, it's not. No, it's not. It's not. It's exactly. This is the point I was trying to make here.
Where? I didn't see any non-compact equation.
No. Look. This addition here with a minus sign means that the symmetry between the advanced and retarded bosonic replicas is hyperbolic. It's a U1, 1.
But U1, 1, but you don't write, you write U1/1.
No, because I looked at the minimal theory where there's, so this thing is for the minimal theory for just one replica, advanced replica or retarded replica. Once I add the two of them together, what I wrote later is this object here, where you can see that the bosonic sector has 1, 1, and that's the non-compact structure. And this is 2 in the fermions. This is just U2. Okay. This 1, 1, is the sort of the notation for the non-compact transformation here.
Okay, so it's even tougher than I thought. Because non-compact symmetries in CFT are really, yeah.
But unfortunately, you have to deal with it here. I mean, it's inevitable.
Don't discourage them.
Sorry?
Don't discourage them.
Yeah. Well, I mean, I don't. I mean, well, I'm just laying out the difficulties.
So I have a question about the schedule of the Friday talk. Is it in the morning or in the afternoon finally?
Well, is any organizers? I mean,
Yes, I don't know. Sylvain was.
Sylvain,
I mean, he was proposing a pool, but we are discussing among organizers.
so
Yeah,
he is.
So, Sylvain, what is your status?
the talk is scheduled in the morning, so we could think of moving it. We have to discuss, well, first to see if it's possible for the involved people.
So, well, Martin, you're the speaker, so probably we should ask you first. Would you be able to give it in the evening in your time instead of, or maybe afternoon instead of the morning?
I just checked my calendar. It looks okay.
I asked Martin.
So I can wake up as early as, let's say, 7 o'clock, maybe in the morning, which would make it, what's it, 1 o'clock in Paris?
Yeah, but you see, I'm going to vacation and I will take a break to especially to hear the talk. And if it's in the middle of my day, then I'm in trouble.
Well, same for me. I'm sleeping during the talk. If it's in the morning in Paris, I'm deep in sleep.
Okay, Martin would be okay with swapping.
Maybe we should conclude the talk, and everyone who wants to leave will leave, and then people who want to discuss the time of the talk will remain and
sure,
we can
absolutely.
discuss with the organizers. Yeah. Who is the chair of this session?
I am.
Yeah.
Oh, which session? This one?
Yeah.
Yeah, I am. Oh, this one, yes. So, yeah, there are other questions. Okay, so well, let me say one thing that the discussion we have had during the question time is basically really in the heart of the goal of this program. So we have had like some targeted discussion. So I'm quite happy about what it came out today. Is what we wanted. So I would like to thank again Ilya for his nice lectures, and we are just starting to warm up, I think, right?
Okay. Yep.
Okay, so well, have a good evening. So I will think that someone has recorded. Yes, finally, I forgot to record. So I will close the Zoom link and the recording. So thanks you to all, and